Thank you for coming. We have, as we did last time, we have a webinar going on this evening. So for those of you who are seeing me through the magic of the webinar, I want to let you know that it's not audio, it's chat. So if you're online and you're seeing me, hopefully you are. Welcome, first of all. Sherry over to my left is going to be monitoring the screen. And if you do have questions or comments, put them in the form of a full sentence. I was told earlier there was an awful lot of free flow of consciousness the last time. Words, punctuation, I don't know what you're talking about. So try and phrase your question as a full question. I guess that goes for the people here live as well. Put your questions together in full sentences. But particularly if you're trying to get to the chat line. And maybe also if you are online, you might just send a chat now and just say, hey, I'm here and this is who I am, just so we know you're alive and well. We're not talking into a vacuum. We've got a really interesting talk tonight, and I want to start by, first of all, thanking you. We are Institute for Ocean Research Enterprise. This is one of our major outreach programs. We do this monthly pretty regularly. The feedback I get generally is that it's very valuable, that it does present a good networking opportunity, a good opportunity for a provocative speaker to throw some really interesting discussions on the floor for question and answer. And hopefully the intent, as our intent overall, is that it spawns more business, that coming out of this is some ideas you walk away with saying, hey, I want to talk to May, I want to develop a new product, I want to collaborate with someone. So that's the intent of the whole thing. You may have noticed yesterday there was an announcement in the press that I want to highlight, and it was all about the province of Nova Scotia taking the ownership of the old Coast Guard base on the Dartmouth side of the harbour. I've been a huge fan of that idea for quite a while, and frankly have put a lot of energy into supporting that concept, and it actually was publicly announced yesterday. And it really does present a big opportunity for industry and academia, and I think government as well, to grow our ocean economy here in Nova Scotia. We're already really quite good at ocean science and technology in Nova Scotia, but I think this is an opportunity to raise the bar even higher. So what hopefully will exist there in a couple of years is a full-fledged ocean science and tech park, ocean incubator, place for interaction on the waterfront with access to docks and boats and shared equipment. So very exciting time. So stay tuned for more information on that as time goes on. And there's other people in the room that I know have been very involved in that as well. So congratulations to all concerned on that one. So without further ado, I want to introduce Dr. May Seto. May is a defense researcher with Defence Research and Development Canada at the Oceanic Lab. She's also an adjunct in mechanical engineering here at Dalhousie. Singularly, when I think of who are the go-to people, the point people on marine robotics, things robotic in our town, first and foremost, May's name comes to my mind. Very engaged from a global level on the research side of performance of robots and their behaviors, hugely compelling professor in the sense that her graduate students line up to kind of be in her class. I think speaks to your passion about the whole topic, your ability as a teacher and as a researcher, and I kind of look to you as kind of our guiding light in terms of where this is all going in the future. So I'm really interested in hearing what you have to say, and I suspect the rest of the audience is as well. And again, I'll remind you if you're online and you've made yourself known, just throw in your questions as things come up. Over to you, May.
Great. Is this working?
Oh, here, May, you can use this one.
I have to lug this around. Oh, God.
Great. Do you want to trade? This one's
Yeah.
There you go.
Great, thanks. Okay, Jim, thank you for the introduction, and thank you for the invite to come and talk to this group. I'm actually quite excited about it. I'm addressing a topic that I'm quite passionate about, so with marine robotics, and I thought the topic that would be most general interest is the transformation value of these platforms. Right, so in the next 20-25 minutes, I'm going to go through an introduction of what the ocean challenges have been now and traditionally. Look at some of the, very briefly, a laundry list of the traditional ocean observation tools that are used. What is the state of the art of marine robots? So what can we do with them now, and what does it imply for the future? Briefly look at exploration versus exploitation. So another way of saying that is saying research and commercial applications of these tools. The transformation, so analyzing that and saying, is that what is the transformation? What direction is it taking us in? And then talk a bit about opportunities to get involved. Right, so the future, and the future is now, it's here, is that the vision you get in watching movies is you've got the lone noble researcher who's going out to sea to look at some problem that's of global importance to everyone. So that's still true. You have lots of lone researchers going out, but that's now given away to a scenario where people come together to fund their cruises. So you would have multiple researchers, multiple disciplines coming together. They've all hired a ship that they'll collectively pay for and then go out and try and get their research done. So the mode of operation, from what I can tell, from what the oceanographers tell me, is they want to have as many measurements as possible per research cruise. Before I get too into things, just to clarify some of the terminology that I use. So terms like measurement, observation, data, sample, they all mean the same thing. We're making a measurement of some type. Sampling is the rate of observation. I'm going to heavily emphasize temporal and spatial scales because it's something that autonomous marine systems or marine robotics can address quite well. The point here being that if you make a measurement here and there, either in space or time, you're not adequately capturing that phenomena. You have to achieve what we call the Nyquist rate, which is a rate that's governed by the highest frequency in your phenomena, how fast it changes, and you choose your sampling rate, whether in space or time, with that in mind. I don't know, how did I turn it off? Is that better?
You have to hold it in for a second.
I have to hold it. Yeah, the battery's probably done. Anyways, I'll be loud. So what you need is you need sufficient resolution in space and in time. And I'm going to emphasize that in what's up here visually with navy colored words every time you see space and time to emphasize its importance. So the ocean environment is a very complex environment to study. You've got the interactions between the atmosphere, the ocean, the land-sea interactions. You've got fluctuations occurring over a wide range of spatial and temporal scales. So you've got a problem that is inherently difficult to capture and characterize. And these temporal and spatial variabilities are not very predictable. Right? It's almost like our weather here. We've got two very strong competing systems, and it makes it difficult to predict what the actual outcome is. So this is a very famous quote from Walter Munk, who warmed a very important chair, the research chair in oceanography for the Secretary of the Navy. Most of the previous century of oceanography could be called a century of undersampling. That's, I think, a bit of an exaggeration, but it captures the essence of what we're pushing towards here, in that you have to sample a phenomena at the right spatial and temporal rates in order to adequately capture it. So the traditional ocean observation tools that people have used and will continue to use include your research ship. So they're vessels for us like the Canadian Coast Guard icebreakers when we go up to the north. They can be very simple devices like remotely operated vehicles, which are essentially robots that are tethered to the ship that the operator is on. Ocean observatories, like some of the oceanographers are familiar with, like Venus and Neptune. Floats, like the Argos floats, buoys, satellites, modeling tools that are built collaboratively from around the world with different components. Manned submersibles are on occasion used as well for ocean observation. And then autonomous marine systems, so what I call AMSs in short. So they're increasingly applied in a wide variety of applications. 5 years ago, you would not necessarily have said the same of that. The applications, military, commercial, and scientific, and in some cases they've transitioned to operational. So for example, with the military, some of the marine robotics have been in use for quite a while, and they're actually getting now fairly mature in their use. They include, as examples, your unmanned surface vehicles. So these are your planing vehicles, your catamaran hull forms, the slocum gliders that quite a few of the oceanographers are familiar with, the unmanned underwater vehicles that are torpedo-shaped, and now what's coming into view for us in the marine world are the unmanned aerial vehicles. And I'll talk a bit about them in some detail. So they can uniquely address the this undersampling problem that people are referring to in the ocean and marine environment. Their advantages are that they are portable, so you can take them anywhere, even to the most remote corners of the Earth, and we've done that, and they're scalable. So if you distribute more of them, you could potentially have better coverage rates. They can support scientific inquiry that's on very large global scales, like global warming, and they can also very quickly zoom in on more episodic events like the algal blooms that are harmful and people want to capture. So those things happen with very little notice. They occur locally, so you have to get your resources marshaled into the area very quickly. Global warming is happening, but it's not at the same short scale. So again, the emphasis on a wide variety of temporal and spatial scales. So what your autonomous marine systems can give you is an adaptable network of sensors. So if you're the kind of person that looks at only the end product, then that's what it is, an adaptable network of sensors that you can distribute as needed. And the idea is that the coverage is good enough that you can complement measurements that you can make with ships, satellites, buoys, or floats. So these are the different varieties of what we call autonomous marine systems or marine robots. You've got the autonomous underwater vehicles, or sometimes they're called UUVs. They're generally torpedo-shaped. So this one in particular is like a remote-controlled submarine, if you like. The twin-hulled HUI vehicles are also AUVs, and they also are very good at very low speeds. So these guys, the torpedo-shaped ones, are good if you're underway, like a fixed-wing aircraft. The Slocum glider, for which quite a few of you are familiar with, has its sawtooth pattern through the water column for sampling and measurement purposes, and a slightly more newer one, the wave glider, which I think Dalhousie has one, is starting to distribute itself actually all across North America. These things are quite impressive. You can send them into a storm and they'll come out of it at the other end of the storm intact, and they would have been reporting throughout the entire interval during the storm. So that's a capability that's difficult to achieve. So these things have, until recently, run scripted missions, which means the operator tells them, you know, first you do step 1, then 2, then 3, but now we're getting beyond that. We have the autonomy to have the vehicles decide on board, these are the decisions it will make to achieve its mission. And you've got the unmanned surface vehicles, so the planing craft, the ones that go really fast and don't have much of a below water expression. The catamarans, which are a little slower, a little more stable at lower speeds, so you can get your measurements made if you want them made slowly and methodically. And then the semi-submersibles, like the Dorado unmanned surface vehicle that the MUOPAR projects here are quite interested in. Right, so to emphasize the difference between them, there is a value to going slow. We've taken these two up to the Arctic for one particular trial, and going through ice and trying to spot the ice, you don't want to do that at 20 or 30 knots because we ripped a gouge in the side of the planing craft, right? So for some things, you do want to go slower. And then there's the unmanned aerial vehicles. So they resemble their manned counterparts. At this point, some of them are still developing in terms of their autonomy, but some of them are also quite advanced. So it depends on the application and what it is you buy and how they are powered. So that's what we call autonomous marine systems for above, just on the water and underwater, right, to fully capture what's going on in the ocean environment. You can also do your taxonomy a little differently. If you're interested in capabilities, you divide it into, so your darker one is the unmanned aerial vehicles, the lime green one's the unmanned surface vehicles, and the light blue one's the unmanned underwater vehicles. So when you have a measurement you want to make, and you have to decide what's important out of payload, endurance, speed, deployment, comms, stealthiness, accuracy of measurement, coverage rates. Okay, so if you want to go really, really fast, you're looking at unmanned aerial vehicles, the dark blue, but they're not necessarily as good stability-wise, and they don't score very well at the moment endurance-wise. That's the ones that run on batteries. The ones that run on air-breathing engines have better endurance. So that's another way of looking at the different capabilities that are encapsulated by your autonomous marine systems. Right. This is just a list of all the different sensors you could put on the more difficult autonomous marine systems, the unmanned underwater vehicles. So integrating the sensor on the vehicle is more than making it small enough to fit within the form factor of the robot. You also have to be able to power it. So the sensor has to be specifically constructed to be very low on power consumption. It also has to be ruggedized so it could put up with the temperature fluctuations, the shock and the vibrations that a robot would incur. And a lot of these types of sensors would be more used to, in a previous time, working from a ship, which is a lot bigger, a little more stable, can give you infinite amounts of power if that's what you need. So these are almost commonplace now to put onto underwater robots. So where are we at with the current UUV? So the UUVs are the ones that are submerged, and we'll say they're the torpedo-shaped ones. In terms of research, they're fairly good at profiling. They're good at looking for objects on the sea bottom. So as most of you know from some of the more high-profile aircraft that have gone into water, they would send UUVs after them. Unfortunately, these particular ones did not find the aircraft, probably because of the types of water they were in. You can also put below water sub-bottom profilers on your UUVs, so you can use them to survey for what's beneath the seabed for exploitation or other reasons. Commercially, they can be used to lay or track undersea cable. So if your undersea cable has moved for whatever reasons, or your undersea pipelines have moved because of earthquakes or other tectonic activity, that's one way to find them. You can use them to help plot your routes for commercial oil and gas. That's fairly commonplace now. The inspection of undersea structures is another important place. So structures like the Hibernia offshore platforms are also always concerned about what the appearance of the platform is below the waterline, because they're concerned with scouring by ice, because Hibernia is in a place where there is a lot of icebergs moving through. And for military applications as well, they're interested in getting the data above and below water, gathering intelligence, deploying leave-behind sensors or other things that are used. All right, so that's kind of the capabilities that are available now. That's not to say they're available for, in terms of endurance, it doesn't mean that they're good for months or years. All right, so going back to this temporal and spatial scale thing, what are we interested in? So gliders are low speed, so they're good for long time scales. Unmanned underwater vehicles are low speed as well, short time scales, but more powering. So the difference between these two would be you could put a more power-hungry sensor on a UUV. On a USV, you have lots more speed. Sometimes you have shorter time scales, it depends. If you have a USV that's powered by an air-breathing engine, it can have a fair amount of endurance by comparison. So as an experimenter, just speaking to the oceanographers, the impact is as follows in your observations. The duration, the fidelity, what is the temporal sampling frequency that's possible given all the different possibilities there, the spatial expanse that you want to cover off, and then the spatial fidelity. How frequently do you need to sample? So they're all affected by the capabilities of these autonomous marine systems in terms of their speeds and their endurance. And then there's a really interesting problem that we're grappling with, and if anybody's got suggestions, if you're interested in all these different scales, so short time scales, long time scales, how do you marry all the data together so that you've got a unified picture of what's going on? All right, so if you've got different phenomena interacting and you would sample them at different Nyquist rates, how do you put all of that together? So that's actually a very interesting project to look at. So at the same time, what are their limitations? All right, so if you've got a robot, regardless of whether it's a marine, space, ground, or air environment, it's carrying its own energy. All right, so everything it has to do for the mission that it was set out to do is completely contained within it. So that directly impacts your endurance and your powering. So if you need a lot of distance to travel or you need to operate for a long time, that generally is only possible with the much larger vehicles. So with the unmanned underwater vehicles, the torpedo-shaped ones, the bigger ones can go further, essentially. So what the whole industry with marine and other robotics are waiting for is for higher energy density batteries to come out. So you can pack more punch within the form factor that you have in terms of energy. And then once you create something like that, then there's another problem of how do you transport such high energy density batteries? Because you can make lithium-ion batteries to very high energy densities, but transporting them is an issue. And then for the unmanned underwater vehicles and for other marine robots, navigation is always a limitation. So if you're underwater and you do not have access to absolute positioning systems, how do you position yourself? I mean, there are methodologies, and we've worked on some of them, but it's a major consideration. And as far as communications is concerned, what are we doing when it's underwater? The underwater medium, as far as acoustic signal propagation is concerned, is fraught with issues. For the bandwidth is low, the range is not very high, and it's very noisy due to multipath and other phenomena that only undermine what you're trying to do. So underwater communications is an issue. Navigation is definitely an issue. And these are problems that are unique to underwater robots. And we're always looking for solutions and ideas for how you can address that. I think it's going to be the chemists that have to come up with solutions for high energy density batteries. So looking at this exploration or observation and trading that off against exploitation, what are we interested in when we're scientists and we're doing exploration or observation? We want tools that are scalable. Again, it has to be scalable in space and time. Portable, again, is important. You have to be able to take it to the remote corners of the Earth. Rapidly deployable is also another consideration. So if you've got something that's quite awkward and requires several ships and lots of people on deck and up to deploy it, you think about that if you're going to take that with you. And for what we're interested in with exploration, it should complement what we can get, again, with ships, satellites, buoys, and floats. So exploitation looks more at, if you've got a robot that's ready and to be commercialized and can be applied or sold to a given market, you've got to look at issues related to how versatile is it. Nobody wants to buy a one mission robot, meaning it can only do one type of survey. You want a robot where you can swap out the different payload sensors and do a variety of different missions and accommodate a wide variety of sensors. Safety is important. Safety has always been important in industry. It should be reliable. If you're going to invest in this as one of your key pieces of equipment for your company, it should be reliable. So that implies it should have a good track record. There's others that I can talk to who've also used it and can vouch for the fact that this is a good piece of equipment. It should be easy to maintain. Right? So you should not have to be a specialist or the OEM or the person who created this thing in order to maintain it. It should be easy to use for the same arguments, because we're not the researchers that created this, and we're trying to sell it to a wide variety of other customers. Field support's important. So if we're out in the middle of the North Atlantic trying to make a measurement and something goes on this robot, can we fly in someone or helicopter in someone to come and give us field support? Because your sea time is expensive. Economical goes without saying, warranties, subsystem interfaces and options available means you can fit it for a wide variety of different capabilities, but not necessarily with it. So it should be options I can buy later. If I want to survey a type A seabed, and I also want to, at a later date, be able to accommodate a sub-bottom profiler, that should be a possibility. And high TRL usually covers off all of these. So this is just a list looking at what you've got here is the traditional ocean observation tools, and here you've got the autonomous marine systems. So this is broken up into the range of the robot, the endurance, and the speed. So we all want long range. Everything we want long range, high endurance, and high speeds. So that's ideally what we are all pushing for. What do you actually get? You tend to find with a lot of the more traditional tools, the range can be shorter. In some exceptions, the range can be quite long. Surface ships can have very long ranges if they're out for long times. And obviously, satellites can have very good range. Endurance is pretty good on some of these. The thing that we're interested in terms of measurements is the sampling and the ability to correlate across different times and different places in the same phenomena. So can we sample for long times? You can with some of them. Large areas, not as easily. So with the more autonomous marine robots, they're slightly better at addressing the what we want. Long range, large areas, high sampling rates in time. Right, so they're not all very good at everything, but quite a few of them are. So they are made for sampling. and adaptive sampling is the important type of sampling that we're interested in. So are they transformational? So are marine robots at this point in history, given what I've very quickly gone over as state of the art, are they transformational? So a disruptive innovation is one that's termed as, you've improved a product or you've dropped the price so low that all of a sudden you're presenting yourself to a new market that's very interested in you. A sustaining innovation does not change any of the new markets. So that's usually something that is very expensive and only a few people can afford. So as an example, the car, when it showed up, was a transformational innovation. Because the car was expensive, the very rich could afford it, and the rest of the masses could not. So the standard for the day, horse-drawn carriage and passenger rail, those markets were not displaced as much. But when the prices on cars dropped, and the manufacturing on them became quite reliable, so maybe not in Ford's words, but they became a much higher TRL product, everybody could afford cars. So when everybody could afford cars, then cars became a disruptive innovation, right? Because then you've displaced the horse and buggy market, and there are less people now interested in passenger rail and getting from point A to B. So let's look at marine robots in that light. So are we at this point in history yet where marine robots are like cars when Ford introduced the Model T to the masses? Well, initially, the marine robots we discussed here were very expensive, right? And nobody would insure them because they were that expensive. So the labs that could afford them were taking their chances, and they were so-called self-insured. So at the time that the unmanned underwater vehicles came out, the work that people proposed that unmanned underwater vehicles could do, like CTD measurements, leave-behind sensors, bathymetric measurements, which are still very important, and monitoring undersea infrastructures, those could be covered off fairly well by ships, submarines, divers, which is good. And initially, when they came out, like when anything else comes out in its early days, they're not necessarily very reliable, and the TRL wasn't very high. And they did not have the independence or the ability to adapt to what was going on around them. So when they first came out, the promise of what these marine robots could do was unclear. And this, again, is not any different from any other technology in its early days. So this has now changed, right? So the unmanned underwater vehicle community, anyways, has matured. They're running, according to other people's surveys, at TRL 7 or 8, right? So they're much more reliable and robust. They're not toys that the researchers play with, and they can be used to do workhorse-type measurements like surveys to look for downed aircraft, surveys to try and track where your missing pipeline went. Right, and the autonomy or the independence or the smarts on board the vehicle has increased to the point where you can leave them for a fairly long time. They've also got more advanced navigation skills given the limitations of not being able to access GPS. So the ability to work under ice with the Explorer missions that we work with, 300 kilometers in one direction and then 300 kilometers back is more autonomy than we had, say, when I started in the late 90s. The market's also made a change in that. So the cost has dropped quite dramatically on the smaller UUVs to the point where universities and most research labs can afford them. Right, so that made a huge difference. And then there's emerging requirements, like we are less tolerant of lost lives if robots can help us mitigate that. We're less tolerant of damage to assets if it's unnecessary. We're also less patient. We like the data to be processed very quickly into information that we can make decisions on. And because we've got good processors, we are indulged. The force multiplication is good. So if you can deploy an AUV out for a couple of hours, and it's the equivalent to quite a few more divers being out for that same time period, that's great. We don't have to put people in jeopardy, and then we can save the divers to do things where you need a human brain to be involved. So are they a disruptive technology? So if you get the autonomous marine systems to do the difficult, the dirty, the dull, the dangerous, so things like mine countermeasures, right? Do you want to send a manned ship into that area, or would you prefer to send a robot? If you can get them to do that, then you can save the ship to do the things that require a human to be in the loop. So you might want to have the human in the loop when it makes the decision, and you definitely do, when they make a decision on what to do with an object that you have found, or help with the identification part. So if you look at it in that light, then yes, autonomous marine systems are a disruptive technology. Right? They'll change the way that we collect data, whether for scientific, military, or commercial applications. So what of surface ships? Right? Have we displaced surface ships because we've got these underwater robots that can make those measurements? By no means have marine robots displaced surface ships. Right? The introduction and the more widespread acceptance of the autonomous marine systems have actually increased the amount that you would use surface ships. So keeping in mind that now surface ships support platforms for autonomous marine systems, the new research ships are being designed with that in mind. How can they support them in the way of berthing, payload, the equipment and the personnel that you have to carry? This concept now that you've got multiple research groups going out on one single cruise to make the most measurements possible per trial. So their design affects that. Their design is affected by that. And the consequence is we're all scrambling for surface ship time. Right? So by no means have these autonomous marine systems displaced surface ships, especially if you're going to go into very remote areas. And currently, very large UUVs or USVs are not usually deployed without a surface ship somewhere nearby. So what this long, detailed drawing shows is the steps that are used when we are working with these autonomous marine robots. Right. So in the end, you're going to be working with an asset that could be on the order of millions of dollars. So what are the steps that you would take? If you're going to come up with a new architecture or bright idea about something you want to implement or an algorithm, you're going to test it out in simulation space. And once you've vetted it in simulation space, you usually test it again on a testbed version of your UUV, right? So not the $2 million vehicle, but the $250,000 vehicle, which in itself is not trivial. So you test it out on the $250,000 vehicle, see if it's working there, and then if it is, then you would consider doing testing and validation on the very large vehicle that costs you a lot of money. And then if it looks like it works there locally, then you would start looking at your client, tasking ships and people and resources to try and take it out to sea to do your big client demo. Right, so that's generally the progression that we have taken. The idea is to mitigate risk. If you're going to create something that you think is very intelligent, has some decision-making capabilities, we want to make sure this is going to do what we ask it to do, even when we give it the ability to make its own decisions and not do something that's completely unpredictable. All right, so for the way we do our research, we employ a fair amount of contractors, and there are partners that are used as well in all stages of that. Right? I mean, speaking for DRDC, I don't know our total research budget, but it's not too bad. We usually advertise through Public Works if we're looking for contractors to help us fulfill requirements at any stage of this evolution with developing them. At the university, there's people who have figured that out in the crowd. You know, if you come and talk to the groups that are interested, there's usually ways of finding money, resources, and people to getting them engaged. Right? So this is not, these problems are very complex. And again, the lone researcher in the corner or in the basement or in the lab cannot solve them. There is a need for a variety of different disciplines and resources to address these problems. All right. So in summary, autonomous marine systems disruptively transform ocean exploration and exploitation. The strength of the autonomous marine system is its ability to adaptively sample at the right temporal and spatial frequencies necessary to do your measurement properly, to capture your phenomena. And the autonomy of these systems, some of the capabilities have been developed and some we are still working on. So again, we're always looking for help. So if you've got suggestions, we're listening. Jim?
Do you think that's achievable in our lifetime?
I'm not really the person to ask for that. That rests with the battery chemists, right? And is it the energy density that makes it for you, or is it the ability for the vehicle to go and hibernate when it's not needed? Right? So there are projects that look at that. right? So that depends on battery chemistry. If batteries is how we're going to, if batteries are the energy sources that are used. Right? So the question that's being addressed is whether long-term endurance on the order of months is possible. I know the U.S. Navy is working on a UUV that they're hoping has an endurance of months. But it would also have periods of hibernation where it's burning energy at a very low rate.
That happen?
Yes, it does. So the question Jim's put forward is one sensor can only measure at one point at one time. So the idea behind the networked autonomous marine systems is that you're deploying many of them, right? And you can synchronize or network them as you see fit. So they've done this. They've taken gliders off of Monterey Bay. They've had, what was it called, Glider Palooza, where they would deploy upwards of 50, 60, 70 gliders into the water simultaneously to do their measurements. Right, so that's if you're covering very long expanses of space at high frequencies in time as well. So I don't know how successful they've been. I think they've published quite a few articles that I've only topically looked at, so I think they've had some success in that. But that is the idea behind their scalability, that you can deploy more of them if you have more space that you have to cover. That's not to say that it's just as easy to deploy one as it is to deploy 5 or 10. There's an overhead that goes with every robot that you deploy, and it doesn't scale linearly. It scales faster than that.
More endurance, more battery?
Well, you always want more endurance and more batteries, right? That's the 3 limitations: the comms, the navigation, and the endurance. So, but if you're talking about a different type of platform, we've got most of what we're looking for at the moment that we can handle. How about that? If other people have other requirements, I'm not going to say that there's not platforms that they would be interested in. I'm not an expert, so the question is about if you've got manned submersibles, so essentially submarines, the comms between them and what they've learned in the time that they've been working for the military, whether some of that could be ported to underwater vehicles. I imagine what could be ported has been ported, and we're now looking at communications between multiple robots underwater. So that problem, you don't usually have multiple submarines, you don't want to have 4 or 5 submarines in the area talking to each other. The area that this addresses is underwater communications using acoustic signals. Right, so I think the industry's done a fair amount to push that forward. Right, so underwater modems of variety of different types and brands have been able to get pretty good progress, but the range that you can get and the bandwidth that you can get underwater is nowhere compared to what you can get with RF. You've got orders of magnitude difference in the speeds of sound. Right, so not being a submarine expert, I don't know everything that they've done underwater. But again, they're not communicating with multiple robots underwater. It's usually the submarine by itself. I guess that stretches your definition of what autonomous means. So if it's unattended, an unattended sensor that can make some decisions is a stationary robot, but it's not necessarily an autonomous robot, because an autonomous robot, through virtue of its motion, can further some objectives of its mission. Right, so if it's an unattended sensor, sometimes they'll call that a robot.
Lots of decisions that have to be made
Yep.
about processing, and there's lots of autonomy in
Yep.
how you organize that processing.
Yeah, but then it's a stationary robot. Right, is it autonomous? It stretches your definition of autonomous. Does autonomous mean that it's mobile, or that it's unattended and you can leave it unattended for months? If you want to stretch to that, then yes, you can call an unattended sensor that has to make decisions on what it does an autonomous robot. So the question that's posed is, what is a sub-bottom profiler? And it's
What do you use? What is used? Is it a chirp type system, or what is the frequency?
that I don't know off the top of my head. It's an acoustic sensor that can make itself transparent to the first couple of meters of the ocean bottom. Right, there are quite a few people in St. John's, if you're interested, I can connect you with them, that put sub-bottom profilers on their vehicles.
Civilian world of Dalhousie, what's your research focus with those graduates?
Our research focus is one of the bigger projects looks at navigation without GPS underwater, because that's the situation underwater. So we do simultaneous localization and mapping. Right, so we've got a fairly large project looking at that. And what that does is it tries to map out all the sensors that the robot sees, and through revisiting a sensor that it saw earlier in its mapping, it can reduce the error in the position for all the targets or objects that have been mapped. Right, so that's a very trite, quick way of explaining a very difficult problem, which is the most difficult problem in all of robotics: land, sea, air, or space.
You're going into a place with no reference points.
You've got no a priori information, no map, and you've got to map the objects that it sees and localize the robot within that map.
Is it mostly all autonomous underwater? They don't need that aerial?
No, we use the aerial ones. I mean, we've got unmanned underwater vehicles that can talk to their surface counterparts, and the surface counterparts can communicate to the aerial vehicles that are aloft, right? Because you can get information from below water to well above water, so that's of interest to a lot of people. Right, so there is that robotic collaboration with below on the surface and well above the surface.